In this video, we present a brief demonstration of our work on multi-perspective simultaneous embedding, MPSE. The paper will be presented by Vahan Huroyan, Raymundo Navarrete, and Iqbal Hossain. The main goal is to visualize a dataset in 3D so that we can see a different interpretation of the data from different viewpoints. One of the main goals when visualizing a high-dimensional dataset is to produce an embedding in lower dimensions, such as 2D Euclidean space that suitably captures pairwise relationships among the represented data. A classical approach for dimensionality reduction is multidimensional scaling, MDS, which aims to preserve the distances between all pairs of data points. There are many popular algorithms for dimensionality reduction, from linear methods such as principal component analysis, PCA, to nonlinear methods such as t-SNE and UMAP. We consider situations where instead of just one pairwise distance function, the input is a set of pairwise distance functions on the same set of objects. The optimization goal of multi-perspective simultaneous embedding is to place the points in 3D so that the embedding simultaneously preserves different types of distances between the objects when projected to different 2D planes.
We now consider a network dataset that captures social relationships between prominent families in Renaissance Florence, one of the largest and richest cities in 15th century Europe. This dataset contains descriptions of social ties between Florentine families during the years 1426 to 1434, a period of historical significance that marks the rise to power of the Medici family and the demise of the Strozzi family. We will be focusing on these two families in this example. The two graphs shown here capture marriage on the left and loan on the right relationships among the families. Each node represents a Florentine family. In the marriage graph, an edge between two families represents at least one marriage between members of these two families. In the loan graph, an edge between two families means that at least one member of one family took a loan from a member in the other family. The positions of the nodes here are determined using multidimensional scaling on the shortest path distances among the families for each attribute. The two visualizations are computed independent of each other, so it is not easy to find correspondences between the two. The node colors indicate the true graph distance from the Medici family with respect to marriage relations and loan relations. Now, we visualize the same two graphs with MPSE. The goal of MPSE is to produce a single 3D embedding that simultaneously represents both marriage and loan relations among the families. This is the result of the multi-perspective simultaneous embedding algorithm. If viewed from the right perspective, the apparent distances between the families are those that best represent marriage relations, as shown here, but if we change the perspective, we get a view that best represents loan relationships among the families, as shown here. Here, we see 2D views of the 3D MPSE embedding along the perspectives that best describe the two attributes in the data. Again, the colors indicate the true graph distance from the Medici family with respect to marriage relations and loan relations. A bit of historical background can help us see some interesting results in a visualization. The Strozzi family had been Florence's richest one, but ended up exiled and in ruin after the Medici took control of Florence's government in 1434. The MPSE embedding allows us a glimpse in this story. The Medici family occupies a central location in both the individual MDS and in the MPSE embeddings. The Strozzi family occupies a similar central position in the marriage perspective, but not in the loan perspective. This reflects the nature of the political power at the time, as both families had strong ties to other prominent families in Florence, but the Medici family was doing better financially by that time. The better positioning of the Medici family is nicely illustrated in the MPSE 3D embedding in a way that cannot be illustrated by the independent MDS embeddings. The Medici family has a central position in the 3D embedding, whereas the Strozzi family lies closer to the periphery. Even though the Strozzi position in the marriage network was firm, their position in the overall network was weaker.
We consider the MPSE problem in two different settings. The first setting takes as input a set of distance or dissimilarity matrices along with a set of projection matrices. The goal of the algorithm is to embed the dataset in 3D such that on each given projection, we approximate the corresponding distance matrix. The second setting takes as input only a set of distance or dissimilarity matrices. The goal of the algorithm is to embed the data in 3D and to find the best projection planes so that each projection best approximates the corresponding dissimilarity matrix. For both settings, we propose optimization algorithms that generalize standard multidimensional scaling. The standard MDS stress function is the following. where the variables are x1 up to xn, which correspond to the possible embedding of the data points. For MPSE, we generalize the stress function as follows, which we refer to as MPSE stress function. Here, the P1 up to Pk are the projection functions. X1 up to Xn again correspond to the possible embedding of the data points. In the first setting, the projections are given and fixed, so we only optimize over X1 up to Xn. While for the second setting, the projections are also variables. For both settings, we use stochastic gradient descent to solve the optimization problem. We would like to mention that MPSE applies to different types of datasets, such as 3D reconstruction, multiple graphs on the same set of objects, and dataset with multiple attributes. We demonstrate MPSE in action using several datasets. The motivation behind this dataset is the 1-2-3 statue by James Hopkins, where looking at the statue from different angles allows us to see different numbers, 1, 2, and 3. For this example, we sample 1,000 points from the pictures of digits 1, 2, and 3. Then we computed the corresponding distance matrices between the points for each image and fed it to the algorithm. The goal is to place the data points in 3D so that under the first given projection, we get to see digit 1, under the second projection, we get to see digit 2, and under the third projection, we get to see digit 3. We also demonstrate the setting where the projections are not specified and the algorithm needs to compute them. As we can see, when in this more difficult setting, MPSE places the points in 3D so that the corresponding projections recover the digits. Another real-world dataset that we use comes from anonymized credit card applications. The dataset contains information about customers of a bank. For our experiments, we randomly select 1,000 customers and focus on 3 parameters: annual income, gender, and level of education. The goal is to use MPSE to embed the dataset in 3D so that 3 different projections show us patterns based on corresponding parameters. Here are the results obtained by MPSE with varying projections. The computed 3D embedding seems to capture well the different perspectives shown in 3 different projections. The gender view shows clearly separated clusters of male, orange cluster, and female, blue cluster. The education view groups customers with similar education levels. See the groups of squares, circles, and triangles. The income view attempts to sort the customers by income, high on the top and low on the bottom, as captured in the change of color intensity from the top to bottom. This view also shows us that education level and income are correlated. The embedding also shows us that the average salary for men is higher than the average salary for a woman, since the orange cluster is placed higher than the blue cluster. Next, we test the stability and the scalability of the MPSE algorithms. We sampled some fixed number of points uniformly from a solid ball with radius 1 in 3D and generate random projections of this data onto our tube. From these projected datasets, we generate the corresponding distance matrices. The input for algorithm 1 are these distance matrices and the projection matrices, and the input for algorithm 2 are just the distance matrices. We consider the following 2 experiments. For the first experiment, we fixed the number of projections to 3 and varied the number of data points between 100 and 2000 in increments of 100. We compute the average running time for both algorithms and the number of times that the algorithm successfully found the global minimum over 10 instances. Here, by successfully finding the global minimum, we mean that the estimated value of stress is within a very small threshold of the actual stress value. The following 2 figures demonstrate the results. As we can see, the running time of both algorithms are comparable and increase linearly with the number of data points. The second figure shows that the increase in the number of data points doesn't affect the success rate of the algorithm. For the second experiment, we fixed the number of data points to be 200 and vary the number of projections between 1 and 20 in increments of 1. We again compute the average running time for both algorithms, as well as the number of times that the algorithms successfully found the global minimum over 10 instances. The following 2 figures demonstrate the results. As we can see, the running time of both algorithms are comparable and increase linearly with the number of projections. The second figure shows that the increase in the number of projections doesn't affect the success rate of both algorithms.
We have developed an interactive tool to access our MPSE algorithm. The tool is hosted at mpse.arl.arizona.edu. We can see some of the pre-computed examples. You can click and interact with the example. If you want to compute live, we can use either our pre-loaded dataset or we can upload our own distance matrix. Then we can set up our experimental parameters and the visualization settings, and then we can start the training. Here I'm going to show one of our example dataset is called circle square, which is motivated by an optical illusion known as circling the square. In this example, we sample 100 points from an image of a circle and 100 points from an image of a square. And then we place it in 3D so that our corresponding projection recovers the circle and square. Let me show how to run this experiment. We select the dataset from here, and then we set up our experiment. We are trying to run this experiment with the fixed projection. Then we hit the button. Then we see the computation is happening, and this is the result. Here we can see the final interaction, 3D positions, and also the final stress. Let me show you the interactive visualization. So this is the final output. You can click on the first button, that is the projection is optimized based on the circle, and the second projection is optimized for the square. Now let me run this experiment again for the variable projection. So I select the variable projection and let me increase number of neighbors 40, and I do not need 200 iteration, maybe 100 is fine. Let's run it. Alright, here is the result. It seems better. So this is the final projection, and we can see this is circle, and this is the final projection for square. We can see this is square.
To conclude, we describe the generalization of MDS, which can be used to simultaneously optimize multiple distance functions defined on the same set of objects. This approach has applications for visualizing abstract data and multivariate networks. Some possible future directions include more experiments and tests of MPSE for 3D reconstruction, and another possible future direction is to check whether similar ideas would work for other dimensionality reduction techniques. Thank you.